and hopefully it gets you to feel pretty confident about finding the both of them. But again, like some of the examples we look at, you're going to say, no, it doesn't have an inverse. And that was like question 61 to 67, determining if the function has an inverse. After you say no, we're going to try and manipulate the function so that it does have an inverse, because a lot of functions don't have inverses. And mathematicians don't like when something doesn't work. We always figure out a way to make it work. So we're going to force functions to have an inverse, even if we might say no initially. Part of your homework tonight is in the book, and it deals directly with the concepts we talked about today with inverse functions and composite functions together. The other part is to begin, and just begin, the chapter 1 review. And my suggestion is to work through 1 through 5 on the review. So I suggest you start 1 through 5. The review isn't due until Thursday. So I suggest you start it, but don't submit the review, not until Thursday. So are there questions on the homework that you had? There weren't really any on the form. I know 73, the inverse actually ended up being the exact same function, which happens every once in a while, where the inverse ends up being exactly the same as the function you started with. Just depends on what the shape of the graph is kind of looking like. But any questions that you can think of?
Could you do problem number 77?
Number 77? Maybe that's
yes.
Yeah, that's the one that I'm talking about. 77. Yeah. So number 77, yeah, let's look at that one. I think that's the one I was thinking, Darby. So 77 gives you a square root function. And it's also, along with the square root function, it says that it's only looking at, oh, come on. There you go. You're only looking at a part of it. So we have the square root of 4 minus x squared. And then next to it, it says 0 less than or equal to x less than or equal to 2. Did anybody graph this? Somebody with a calculator? Peter, you got yours on your desk thing. So the first thing that we want to look at before you do any problem, if you're determining inverses, is to graph it and check to make sure it has an inverse. So that's like step 1. Look at the graph, graph it in your calculator. Does it have an inverse? All right, Peter, did you get it?
Adjusted the window, so it like starts at positive like 0, 2, and then it kind of curves down to 2, 0.
Like this?
Yeah.
So if you initially graph it when you put it in your calculator, the entire function is almost like a semicircle. That's what the entire function looks like. But Peter said he adjusted his window to only show the portion that we're looking at. And the portion we're looking at is when x is 0 to x is 2. And the reason we're doing that is because right now, the semicircle doesn't have an inverse. And we're going to look at problems, again, similar to this. So they're only saying, look at the problems, or look at the points from 0 to 2. Now it has an inverse. The whole thing didn't, but just this little portion of it does. So now I have like a fourth of the circle instead of having a semicircle. So since it has an inverse, I can continue to find the inverse following those steps from yesterday. So step 1, make it y equals. Step 2, switch x and y. So now this says x equals 4 minus y squared. And then I continue working and trying to get x by itself. So Joe, how would you get y by itself here? Yeah, square both sides. Now we have x squared, 4 minus y squared. Joe, what else did you do to solve?
Add y to the other side and subtract x.
Perfect. So he said add y to get the y on the left. Subtract x. And then finally, Joe, you would square root both sides. So once I take the square root, usually we have a plus or a minus because you took the square root. When you take the square root, you're applying that plus or minus. And then we have negative x plus 4.
It's not that, but you subtracted it.
Yeah, I actually was just looking at that. Thank you. So the last little part here, because you took the square root, we have that plus or minus. We have to pick either the plus or the minus sign. And the one you choose is based off of your given graph. So our given graph is positive. It's above the x-axis, and we'll talk more about this today. So I would choose that plus sign. So my inverse has to correlate with the graph that we're given. So my inverse is going to be the square root of negative x squared plus 4. But if you look at this inverse, let me make it an inverse, and compare it to the original function, what do you notice about the original function and the inverse? They're the same. So the original function was 4 minus x squared. I have it written now as negative x squared plus 4. They're the same. I have the same exact equation, and that happens every once in a while for inverses. Now, it has to directly correlate with my initial information I was given. So this restriction that was on x, I have to have that same restriction in my x as well. It has to match the original equation. And again, we're going to look at another example or two like this. So I have to kind of put that restriction on there. One, because I have a square root, and I can only have specific numbers underneath the square root. But two, because the graphs have to match each other. So if I only have a piece of this graph, my inverse has to have just a piece of it as well. I can't have the whole graph because my inverse should directly mimic the graph that we have. Questions on that? Good question to ask. As I said, we'll look at a couple of more of these as well. All right, so we're going to go into your notes, and this is still section 1.6, but it should say day 2. And as I said, we're going to start off with a warm-up problem, finding inverses and composite functions. We're going to look at 2 examples where it isn't initially an inverse function. It doesn't exist, but we're going to work with that restriction part and see how we can restrict it so that it does have an inverse. So we're going to kind of look at that. So the warm-up gives us 2 functions, f and g. And then it has the inverse notation, also the composite notation. So the notation over here says the inverse of f with the composite of the inverse of g. That's how I'd read that. So instead of saying f of g of x, I'd say the inverse of f of the inverse of g of x. Whole bunch of words, lots of words. What do you think you'd do first? Peter? We have to find the inverses because this is using the inverse function. We're taking the composite of the inverse functions. So see if you can find the inverses of both of these equations, or both of the functions. So we have to use the inverses first. So again, set it equal to y, switch x and y, and then get y by itself. Make sure that you're using inverse notation. So I now have the inverse for my f function using that inverse notation. Same thing with G, make it Y equals, switch X and Y. G is a little more interesting. Jack, how would you solve the inverse for G?
X cubed plus 2.
So the inverse of G, he said, is X cubed and then plus 2. Again, like inverses are opposites. So if I have a cube root, my inverse then would be X cubed. We were subtracting 2, so now we are adding 2. All right, so we got the two inverse functions. Now we're going to use those two inverse functions and take their composite. So we're taking the composite of the inverse functions, not the original functions that we were given. So it says have f, the inverse, and then inside is g inverse. Well, g's inverse is x cubed plus 2. So we're not using those original functions, we're using the inverses we just found. So in place of the inverse function, here's my inverse function. We're replacing x with our g inverse. So instead of saying x minus 1, it's going to say x cubed plus 2. There's my inverse of g, and then still minus 1. So the inverse of f with the composite of the inverse of g of x, pretty wordy, is x cubed and then plus 1. That's just an application, kind of using inverses as well as composite functions. And again, some of the problems that you'll see today are going to have similar concepts, processes. Questions?
Mrs. King, could you cube root both of those?
Say it again.
Could you do like the SOAP method of factoring, or would we just
Oh,
leave it
you
like
could,
this?
yes. To factor it, you totally
Okay.
could, yes, because this is a perfect cube. You don't have to.
Okay,
But yes,
thank you.
nice job noticing that. Yeah, so these are perfect cubes. So she's saying, let's factor this, which I awesome for thinking that it is factorable because it's a perfect cube. So the SOAP formula, but you can leave it like that too.
Why would
Any
the
other?
x cubed be cubed? Like it's not cubed whenever it's under the radical, but do you cube it since you're flipping it?
Yes,
whenever
so up
Going
here,
inverse.
so because we are finding the inverse function, in order to get rid of the cube root, we have to cube both sides to get rid of the cube root symbol. So that's just finding the inverse. So the first step, because we're using the inverse here, the notation, we're using the inverse. And in order to get rid of the cube root, we have to cube both sides. So that's how x becomes cubed.
Okay.
To get rid of the
Okay. That makes
other
sense.
questions. Nope, thanks for asking. Any others? So finding the inverse and then using the inverse functions, not the original functions, to do the composite. So we are going to look at two different functions that initially would not have an inverse function. So if I look at the first one, it says determine if the function or whether the function is one-to-one. And that's what you need to do first for all of these problems. So if you're given a function, the first step is determine if it's one-to-one. Because if it isn't one-to-one, then it doesn't have an inverse. So Parker, thinking about this graph, we have the absolute value of x minus 2. What's absolute value look like? A v. What does this minus 2 do to the v, Parker? I'm not translating. How's it translated? To the right. Yeah, this graph is moving right to. Remember, x minus 2. X minus is the formula. The 2 is saying shift right to. So I'm going to make a little sketch. We don't need to rely on the calculator for absolute value. Parker told us it's a v. Our v moves to the right too, and that's where its vertex is going to be located. And then it just has a slope of 1. It's a standard absolute value. I'm not gonna worry about plotting a whole bunch of points. I just plotted where that vertex would be. So Parker, if I look at this graph, determine whether the function is 1 to 1. Is an absolute value function 1 to 1? No, it isn't. It's not 1 to 1 because it doesn't pass the horizontal line test. So I would say, no, we can't find an inverse. Except this piece right here. Or maybe not. Or maybe it's frozen. We'll just let it think for a minute here. There we go. So it's saying that in this function, we're only going to pick the part where x is less than or equal to 2. So right here is where it is 2. Which side of that is less than or equal to 2, Cole?
The left.
The left. So I'm going to kind of make now a piece of this graph, like those piecewise functions. I'm going to erase the side that doesn't exist. So I still have the original function. It was an absolute value, but I took the side that doesn't exist and I took it away. Cole, now would it have an inverse?
Yeah.
Yes. Now it's 1 to 1 because I'm only looking at half of the graph. So this is 1 to 1. It's only 1 to 1 because we're looking at just that half of the graph, the half on the left. All right, so now it says, let's find the inverse. And we're dealing with an absolute value function. So if we're finding the inverse, the first step is to make it y. The second step is to flip x and y. So I'm going to write it over here. X equals, keep those absolute value bars, absolute value, y minus 2. Now, chapter P is where we solved absolute value equations at the very beginning of the year. Leah, do you remember what to do with those absolute value bars so we can solve this equation?
No.
What do we do when there's absolute value bars? Olivia, do you remember?
Would you do the equations so that one's like plus and one's minus?
Exactly. So when you have absolute value, remember, in order to solve for absolute value, you split it up into 2 separate equations, one that's plus and one that's minus. So we're going to take this and split it up into 2 separate equations. The first one stays the same. The second one gets the negative x, and we apply the negative on the other side of the equal sign. So I would say negative x equals y minus 2. Now, before you solve, if I look at my graph has one piece. My answer has to correspond with the graph. Which one of these answers do you think we would be using? Or which one of these equations do you think we would be using? Because I don't have both. I just have a piece.
Would it be the one where x is negative?
Why would it be the one where x is negative?
Because you look at the graph, and it has a negative slope.
Yeah. So we're not going to use both equations because I don't have both pieces of my absolute value graph. I just have the one with the negative slope. So the equation we're using to solve the inverse is the equation with the negative slope. The equation that correlates with the left side of the graph. So now, not using this one, continuing to find my inverse, I would take the 2 to the other side. Let's flip it over here. And write it in inverse form. So f negative 1 and then negative x minus 2. How about plus 2? Make sure I took it to the other side. Questions? All right, the problem is not quite done. Because if I have negative x plus 2, that's an entire line. My graph is a portion of the line. The current graph is only the piece of the line where x is less than or equal to 2. So I can't have this entire line because a graph of an inverse has to match the graph of what you have. So I have to figure out what piece of the line this is going to kind of correlate with. If you look at the given function, they told us x is less than 2, less than or equal to 2. That's the x values. What would the range of this function be? So this is technically the domain. What would the range of this function be? Peter?
0 and 30.
Right, so we would say x is greater than or equal to 0. How about y? Come on, Mrs. King, get that range right. Yesterday, we said something specific about the domain and range of the function versus the domain and range of the inverse. Does anybody remember what we said yesterday? How does the domain of the function compare to the range of the inverse? Or how does the range of the function compare to the domain of the inverse? Anybody remember what we said?
The range is the domain of the other.
The range of our function becomes the domain of the inverse. So we use the part of this line where x is greater than or equal to 0. That's really hard to think about. And that's because I can't use the entire piece of this line because the entire line goes on forever left and right. Whereas the graph that we're given is like half of a line. So I need to pick half of a line in my answer when I find the inverse. And the piece that you use is the range of the original function. Because the range of the original function becomes the domain of the inverse. Questions? We're going to do another one. All right, so let's try this again. Let's look at the next one. This one now tells you to delete part of the graph or of the function so that the part that remains is 1 to 1. And then it says, find the inverse of the remaining part. Find the domain of the inverse. So we need to give that domain so that we have the correct piece of the graph. All right, so let's look at this graph first. Again, I'm going to make a little sketch. Sometimes a picture helps understand what we're looking at. So Cole, if we have 1 minus x squared, what does that graph look like?
It goes up 1 and it's parabola down.
Nice. So moves up on the y-axis and then a parabola facing down. So I'm worried about the vertex here, making a parabola facing down. All right, that was step 1. I graphed it. Now it's telling us to delete part of the graph so that the function that remains is 1 to 1. How do you think you delete part of the graph?
Could you like make an inequality for the domain or something?
Yeah, so we're going to add a little extra part. We're going to make a little inequality to show us what part you're keeping. Peter, what part do you think we could keep?
The right side.
Yeah, probably easier to keep the positive side than the negative side. But starting with the vertex, that's where the graph is cut in half. So based off of the vertex, pick 1/2 of the parabola. It's probably easier to pick the positive side than it is to pick the negative side. So we'll say x is greater than or equal to 0. Now, before I find the inverse, my x is greater than or equal to 0 because here's the x. It's at 0. And I'm picking the right side, the positive side, the part that starts where x is 0. But let's also write the range because we're going to need that range eventually. Whoa.
Don't do that.
Jack, what's the range of this graph?
Negative infinity to 1.
Yeah, negative infinity to 1. So he said negative infinity to 1. So if I write it in interval notation as Jack gave me, so that's the range. And here's our domain. We could also say 0 to infinity. All right, so I'm gonna delete part of the graph. It's gone. Woohoo, I only have the one side. And now we're gonna find the inverse. So I think finding the inverse is the easy part. It's kind of understanding what it means. That's the harder part. Like when you're deleting part of the graph. So first step, make it y equals. And then start solving. So I know I have to get y to the left, x to the right, and then I have to take the square root. So this is very similar to number 77 that I think Darby asked about. When I solve this, anytime I take a square root and place it in an equation to solve, my answer is plus or minus. The reason it's plus or minus is to kind of correlate with my original graph. Because my original graph has a positive side and a negative side. Peter chose to keep the positive side. So that means, Peter, in your inverse function, we need to keep the plus sign. But if Peter kept the negative side, then in the inverse function, we would have to keep the minus sign. So this plus or minus corresponds directly with the original graph. It has a positive and a negative side. So we are choosing the positive side because Peter kept the positive side of the graph. But if you said, I don't want to keep the positive side of the graph and I want to keep the negative side, then my answer for the inverse would have to be the negative piece of the graph. And then the last part, it says find the domain of the inverse. The domain of the inverse is the range of the original function. They are correlated directly together. So what was the domain of one becomes the range of the other. What's the range of one becomes the domain of the other. And that domain is negative infinity to 1. And if you look at the square root, it makes sense because I have a negative underneath the square root attached to my x. That means my x values need to be negative in order for us to take a square root because there's already a negative with the x. So the only way my x values can become positive is if I choose negative x values as well. Any questions? I know that's like, it is kind of weird, it's different. But if you start with the original graph, list the domain and the range of the original graph. That's where you begin. So that when you write your inverse function, you're then using the range of the new or the original function to become the domain of the inverse. Any questions? So when it's not an inverse, we delete part of it. When it doesn't have an inverse, it's not 1-to-1. Delete one part based off the vertex. Usually they're going to be absolute value or they're going to be parabolas. So delete one side. Make sure that one side then correlates with the side that you're using for your inverse function. Does anyone have questions? Okay, so the last type of examples that we're going to look at are very similar to the warm-up examples that we did. And this is part of the homework that you have tonight. So the first two problems of your homework are like these two examples. You're going to delete part of the graph. That's the first two problems, 81 and 83. The other group in your homework is going to be like the next page of notes. So we have two functions, and that's how your homework is. It's going to give you two functions. And then you're going to be asked to use those two functions and different applications of those two functions. So use the two functions, 1/4 x plus 5 and g of x is x cubed, to find the indicated value of the function. And I have, I think, 6 examples here. Yeah, we probably won't get to all 6, but we'll do a couple of them together. So before you start any of the problems, if you just look at the notation, Cole, what do you notice is the notation in every single one of these problems? It's all -1, and that -1 means the The inverse of the function. So what do you think you should do with those two equations? Get the inverses for both. So tonight, when you start your homework, before you answer any of the questions, we need the inverse functions of them because the notation here, we're going to be using the inverse functions. So I'm going to start off by getting the inverse for both of them. So that's the first step that I would say to kind of work on.
Wait,
Yep.
For A and B, are they the same like equation or like for A, do you find f of g and I find the inverse of, okay, so
Yes.
it's not like, so it's not the inverse of f.
Correct. Yeah. So the notation is slightly different. Yeah. We're going to talk about that. Yeah. So I'm just finding the inverse first. That's going to be the first step I do. Figure right. So switch x and y. Solve for y. Be really careful when you're solving for y here. Jack, what would you do to solve for y? So x minus 5 equals 1/4 y. How would we solve for y?
Divide by 1/4.
Oh, I want to divide by a fraction. How else could you get rid of the fraction?
Multiply by 4.
Yeah, let's multiply by 4. But when you multiply by 4 on the other side, what does it become, Jack, if I'm multiplying this by 4?
4x minus 20.
Yeah, just be really careful that you're multiplying all of it by 4, not just the x. So my inverse for f is 4x minus 20. So we subtracted 5, multiplied everything by 4, so we end up with 4x minus 20. If we want to find the inverse of g, this becomes x equals y cubed. So Olivia, to solve for x, or I'm sorry, to solve for y, you would
do the cube root instead.
we would do the cube root. Because it's y cubed, then I need to get y by itself. So the inverse of g is the cube root of x. All right, so I have that part over here so that I use it eventually, or maybe I need to use it now. We'll kind of look and see. So these are my inverse functions. Here are my original functions. So right here, my original f, my original g. All right, now we need to kind of talk about what this information means, the notation means, and this is what Peter was asking about. You look at A and then look at B. They are written differently and they mean something differently. So A has parentheses, and inside the parentheses, it says f of g of x. When you have parentheses, order of operations says you've got to work inside the parentheses first. So if I look inside these parentheses, this is f of g of x. We need to do that part first. The part on the outside, that's the inverse. We're going to take that part last. So the two functions that you're using here, Peter, are what?
1/4x plus 5 and then x cubed.
Right. So you're using the original functions first in this problem because it says f and it says g. The notation outside is last. So I'm going to look just inside and do the composite of the regular functions. So g is x cubed. If I apply that to f, I get 1/4 x cubed plus 5. So that is f of g of x. That's the inside. Now, Leah, what do you think you're going to do with this composite? We find the inverse of this equation. So we found the composite first because that's what's inside the parentheses. Now we're going to find the inverse of this equation. So now I switch x and y. and then I solve for y. So I subtract 5. I have to multiply by 4 first. And we said multiplying by 4 affects the whole thing. So 4x minus 20 is equal to y cubed. And then we take the cube root. So the cube root of 4x minus 20. Is my composite of the two functions, and then taking the inverse of that composite. So we looked on the inside and looked at the notation, and then we applied the outside. So we did the inside first, and then we applied the outside. If you look at letter B, it's written completely differently. G is first, and it has the inverse directly attached to the function. And then it says of f, and it's the inverse, again, directly attached to the function. If I rewrite this, this is saying take G's inverse with F's inverse, and then the X. So different notation. Holy cow. I gotta fix that clock. So do the inverse functions here and use the composite. I thought I had 3 more minutes. Have a great day. I will see you guys next Monday. Remember, tomorrow everybody is virtual, so we'll kind of work through some problems together tomorrow. You'll have some time in class to ask questions and then work on reviewing for the test and practice.
Good day, thank you.
Thanks, see you later. See you, cool, have a good one.